Hello, my name is Lucas, and I'm a Principal Solutions Architect at Amazon Web Services. Thank you for joining this IT Administrator session, in which we'll be talking about how you can improve the performance, observability, and reliability of your applications by introducing one of our latest service announcements. In order to do so, we'll start by setting a bit of context on the history of distributed applications, which will lead us to introduce the testing practice known as chaos engineering. And finally, we'll have a comprehensive overview of the AWS Fault Injection Simulator. Alongside the presentation, we'll have a couple of demos and some final remarks at the end of the session. So what better way to discuss distributed systems than using Amazon as an example? Back in 2001, Amazon.com was a monolithic application deployed as a single artifact. As an IT administrator, this has a lot of benefits such as consistent deployments, known bottlenecks, consistent and predictable scaling. But in 2009, a decision was made to decouple this way of working in favor of multiple discrete, single-purpose applications known today as microservices. With this approach and the right setup in place, there are many benefits: speed to market and rapid delivery, easier scaling and improved collaboration. IT administrators, however, understand the complexity behind ensuring this is all done properly. And that's because distributed systems are hard. In fact, even simple applications are complex. Take, for example, a simple client-server communication. There are lots of steps involved to successfully complete a round trip. It is mind-boggling to consider all the permutations of failure that can happen in this simple distributed system, especially over multiple requests. So imagining how it looks for thousands or millions of requests. The traditional way to tackle this challenge has been testing. But as distributed systems have grown more complex, testing has reached its limits. And often, we only implement tests after outages have happened in production. And of course, that is too late. Testing, of course, is mandatory, and you shouldn't stop doing it. But it doesn't apply well for distributed systems, and often doesn't address the complexity of production environments. Testing tests things in isolation, and testing really only verifies for known conditions. Tests answer questions like, is it what we are expecting? Is the result of that function too? What about random failures and other weird errors that happen on networks like the internet? What about configuration limits? Drift? What about the unknown? How can you test something that you don't know yet? So chaos engineering is the process of stressing an application in testing or production environments by creating disruptive events, such as server outages or API throttling. Number two is observing how the system responds. And finally, is implementing on those improvements. And we will do that to prove or disprove our assumptions of our system's capability to handle these disruptive events. But rather than those events happen at 3 a.m., during the weekend, in production, we create them in a controlled environment and during working hours. It is important to note that chaos engineering is not just about improving the resiliency of your application, but also its performance uncovered hidden issues, exposed monitoring, observability, and alarm blind spots and more. Improve recovery time, improve operational skills, culture, etc. It is also very important to understand that chaos engineering is not about breaking things randomly without a purpose. Chaos engineering is about breaking things in a controlled environment through well-planned experiments in order to build confidence in your applications and tools you're using to understand and withstand turbulent conditions. To do that, you have to follow a well-defined scientific method that will take you from understanding the steady state of your system that you're dealing with to articulating a hypothesis, running an experiment, often using fault injection, verifying the results, and finally, learning from your experiments in order to improve the system. Improvements such as its resilience to failure, the performance, the monitoring, the alarms, and the operations. However, while chaos engineering is a great option to have in your toolbox, our customers have told us that they feel it's hard to get started with. It's hard because currently you have to stitch different tools, some scripts, libraries all together to cover the full spectrum of the faults that you can inject into a system. The infrastructure, the network, the applications, each have different tools to do the job, whether it's a library or an agent. Customers often don't want to install anything extra in their applications, because the more things you install, equals to more complexity. It is also difficult to ensure a safe environment in which to inject faults. Ideally, you want your tools to automatically stop and roll back if any alarms are setting off. You also want this to integrate nicely with the monitoring solution. And finally, some failures are simply really hard to reproduce. It is important to realize that outages rarely happen because of a single failure. It is often a combination of small failures happening at the same time or in a sequence, and that's really hard to reproduce. So this is the architecture for the application that we're going to be using today for our demos. It is a statically hosted website that acts as a book search engine, and it integrates with a couple of microservices that are hosted in managed and unmanaged services. Okay, so here we are on our demo site. As we discussed before, it's a book search engine. We can enter our search criteria, but also search by different type of search functionalities. So we got author names, we got title names, and we also have ISBN numbers. So if we go ahead and we enter an author's name, we can see that we get a whole bunch of data back from our API. Data such as the title, the published year, and the ISBN number. We can also get some more information that is hidden in the UI, such as the publisher. And we see that once we enable that, we can see the publisher in the UI. Because we're getting many results back, we can also do some pagination. And then we can go ahead and search for a different author. And as you can see, every single piece of functionality in this demo is backed by different microservices. So as a true distributed application, hopefully the disruption of one of those microservices can withstand the failure of the entire system. We also want to have a look at how things are running behind the scenes. And I'll show you, how all these different microservices are being set up. So in here, we are in our Elastic Beanstalk environment. We're using Elastic Beanstalk for one of our microservices. We can see that the health of the environment is green or okay. If we wanted to see some of the configuration details for this system, we'll head into the configurations. And we can see that we're running a minimum of 1 instance and a maximum of 4. So this will be quite relevant in our second demo. As we take down that instance, we'll see what happens to the entire environment. There's also the monitoring of the system. And as we can see from here on the monitoring tab, it's all running okay. And we'll also see in our second demo, as we're running some experiments, how that affects the different monitoring values that we're getting back from our system. So this is one of our microservices. If we can see, we're also using a database behind it. This comes in the form of an RDS instance. And we can see that we're also not using the multi-AC functionality. So this is good to know that as we're using managed services, we also need to be mindful of whatever configuration we apply to it. Finally, our last microservice is a container running on Elastic Container Services, or ECS. And we can see we have a cluster here. And this particular task is currently healthy and running. And we can see also as well how the cluster also is running behind the scenes. So in here, we can see all of our EC2 instances that are currently running. One is for the Elastic Beanstalk environment, and one is for our ECS cluster. We can see they're both passing their status checks, and they're healthy and active, and that's it. So let's do a recap of what we've seen so far. We started with a high-level overview of distributed architectures, and then we move on to introducing the chaos engineering testing practice. Finally, I'll show you an application that we'll be using to run some experiments later on. So first of all, let's talk about the AWS Fault Injection Simulator. The AWS Fault Injection Simulator, our fully managed chaos engineering service, is an easy-to-get-started service which lets you reproduce real-world failures, whether they are simple, like stopping an instance, or more complex, like throttling an API. AWS FIS fully embraces the idea of safeguards, which is a way of monitoring the blast radius of the experiment and stopping automatically if alarms are setting off. Getting started with the service is very easy. This is something that we have put a lot of effort into since our customers have repeatedly told us that it was hard to get started. You can use the console to get familiar with the service, try things out, and then you can use the CLI to take advantage of templates and integrate the service with a CI and CD pipeline. The templates are JSON or YAML files that you can share with your team. You can version control them, and then you can benefit from all the best practices associated with a code review. So you can run your experiments in sequence or in parallel. Sequences are used to gradually test the impact of gradual degradation, like sequence of actions to gradually increase latency, and parallel experiments are to test the impact of multiple concurrent issues, which is often how real-world outages happen. Supported services are EC2, RDS, ECS, and EKS, and more will follow, so you can create complex conditions that span across a large set of AWS services. Just to make it really clear and hit the nail on the head here, these faults are really happening at the service control plane level. An instance is actually terminated, memory is actually being utilized, and APIs are actually being throttled. We are not faking it with metric manipulation. So we have to use extra caution when using this service. Safeguards act as the automated stop button, a way to monitor the blast radius of the experiment and make sure that it is contained, and that failures created with the experiment are rolled back if alarms goes off. IAM controls can also be used to control what fault types can be used and what resources can be affected. For example, using tag-based policies, such as saying instances with the tag of environment test can only be affected. So here you can see the architecture diagram of the service. You can currently use AWS FIS using the console or the CLI. The console is great to get started and try things out during a game blade, for example, and the CLI lets you automate things out with your CI and CD pipeline. AWS FIS integrates with IAM policies and roles, so you can be sure that only authorized parties can run experiments. You can also define more fine-grained controls, for example, what types of faults are authorized and on which resources. When you can create your chaos experiments from the console, FIS automatically creates a template for you, a template that you can reuse later on. Once you start your experiment, FIS injects failures, real failures, on your AWS resources. It is best practice to have CloudWatch alarms monitoring your AWS resources and workloads and define some stop conditions that will automatically stop the experiment if they change status. Finally, you will be able to integrate your own monitoring solutions via Event Bridge in order to trigger stop conditions. To use the service, you only need to understand these 4 components: actions, targets, experiment templates, and experiments. So let's take a look at each of one of them and let's see how they do and how to define them. Actions are the fault injection actions executed during an experiment. You will use these to define what type of actions you want your experiments to run. Actions include a fault type, a duration, targeted resources, timing relative to any other actions, fault-specific parameters such as rollback behavior or the portion of the request to throttle. So this is the JSON representation of actions. Here we have 2 different actions defined: stop instances and terminate instances, each with different targets. Notice that terminate instance is ordered to execute after stop instances. This is a sequential experiment execution. It is worth noting that some host-level actions on EC2 instances are performed through the AWS System Manager's agent. The SSM agent is Amazon software that is installed by default on most Amazon Linux and Ubuntu images. I will show you the integration during the demo. Targets define one or more AWS resources on which to carry out an action. You define targets when you create an experiment template. You can use the same target for multiple actions in your experiment template, and the targets include a resource type, the resource themselves through resource ID, filters or tags, the selection mode, how many of the resource to target, all, a random selection, or a fixed count. In this JSON representation of targets, we're using filters to target only instances that are running in one particular availability zone. But that's not the only filter here. Notice how the use of tags to refine the selection. I would say that it's best practices to always use tags, and in this case, only the instances tagged with purpose chaos.ready will be targeted. It is another safeguard mechanism to prevent mistakes. Experiment templates define an experiment and are used in the start experiment request. Experiment templates include the actions, targets, stop condition alarms, IAM roles, descriptions, and tags. So a template looks something like that. Again, you can use JSON or YAML as you prefer. You have the name using tags, the description, the IAM role, the stop condition, the targets, and finally the actions to perform on the targets. Finally, experiments are a simple snapshot of the experiment template when it was first launched. It is your history of experiment execution. It has information on top of the snapshot, the creation and start time, status, execution ID, experiment template ID, and the IAM role identifier. Okay, so here we are on our second demo. I just wanted to give you a quick reminder of what's running behind the scenes. We got our two EC2 instances, one from Elastic Beanstalk and one from Elastic Container Service. The health of our environments is all green and okay. And we can see that our APIs are returning the right data. If we look into our clusters, everything is active, running in green. We have our FIS service here that is in charge of running our task. And as we can see, we have a desired number of 1 and a running number of 1. And if we come into the auto-scaling groups, we can see the auto-scaling group that ECS is using. This is the one in charge of managing our EC2 instances. And this is the AWS FIS homepage. So we can go ahead and create an experiment. We'll give it a name. Then we'll select the role that we use to execute our experiment. Then we need to start looking at creating some actions. So we can go ahead and select the Add Action button. Same as the template, we have to give it a name. Ideally, I'll recommend you to give it a descriptive name. So instead of calling it the ECS API, we'll just call it the Stop ECS API. We'll select the type. In this particular case, will be a stop instances from EC2. And FIS already creates a target group for us. So we go ahead and save that action. We're going to create a different action now. And this will be for our Elastic Beanstalk API. And instead of stopping this instance, we'll be terminating it. In this particular case, we can define whether we want to run it after or at the same time. For this particular system, it doesn't really matter, but for demo purposes, we'll just make it run after. We'll go ahead and save it. And now on to modifying our targets. Again, I'll recommend you giving it a descriptive name. As we can see, our target is of the right resource. In our target method, we can select them either via ID, which will go and fetch now. So if we see here our EC2 instance, the ID will go and grab that. We'll make sure that we select the right one, and that will be the one that we'll be stopping. The selection mode of all count doesn't really matter because we're specifying a single instance. And now we need a different action group, a target group. This will be for our Elastic Beanstalk environment, which is also an EC2 instance. And instead of doing it by ID, we'll do it by tags and filters. We'll say that we'll select all of the instances that are matching the criteria. And we want to do it by name. So if we go back to EC2, we'll grab the name of our instances. Just copy that value. And we can also add some resource filters. For this particular example, I only want to run these experiments against running instances. So I can go and specify that the state should be running. Go ahead and save that target group. And now we need to update our actions to make sure that they're pointing to the right targets. So our ECS API action is pointing to the ECS API target. And our Elastic Beanstalk API, we need to change it to target to the right target group. Change that and save it. Again, it's always recommended to set up stop conditions. We won't be doing that one for this particular demo. But in production environments, you want to have the safeguards in place. Go ahead and create an experiment. And now FIS is giving us a nice warning again that if we're completely sure that we want to create this experiment, and we can see here that the experiment has been created, and we can go ahead and run it if we wanted to. If we wanted to run it, we can assign it some tags. And again, FIS wants us to be completely sure if we want to run it again, because as we talked before, this is not a simulation, this is actually running against your resources. So we go ahead and confirm. And now experiment template is running, and this has created an experiment execution. We can see the status, we can see the role, and we can see the ID for this particular experiment. Because we're running it in sequence, we can see each action's status. They're both currently pending at the moment. We can also see for this second action that it's a sequential action, and it's only going to run after the ECS action is complete. You can also go into the Targets tab and see into further detail what are we selecting and what are we running against. And if we refresh our experiment, we said now it's completed. We can see both actions are green, and we can see what this has done to our EC2 instances. So as we refresh the EC2 homepage, we see that there are no running instances. And as we expected it, if we refresh our Elastic Beanstalk environment, the health of the environment is unknown. The API now is returning a service error. And as you can imagine, that's because we define it as one instance. Our ECS container services is still running the service, but the task is not actually running. That's because there's no EC2 instance to run the task on. If we see here, even though we got two EC2 instances showing up, we see that they're not running the ECS agent. And this is because they are not valid EC2 instance for the service to use. As we refresh, we see that a third instance has shown up, and it's actually running the agent. So we can start seeing behind the scenes some of the auto-scaling groups actions. After some time, the running task will be up there. So if we refresh our auto-scaling group to see what ECS is doing behind the scenes, we see there is a new EC2 instance. If we go into the Activities tab, we can exactly see what's been happening. And we can see that an instance has been removed from the group because it was unhealthy. And then we can also see how a new instance was included into the group. If we go back to the EC2 homepage and refresh, we now see that the two instances that we need are coming back online. They're still initializing. That might take a couple of seconds to finish. If we go back to our Elastic Beanstalk environment, we now see that it's all green. And that's because we added a new instance that we just saw before. We can also see the monitoring of the environment. And we can see for that specified time, the moments in which the state of the environment changed from OK to unknown. For the ECS cluster, we'll see the service will eventually run a task. That's because the ECS EC2 instance is still initializing. Again, if we want to see all the experiments that we've been running, we can see them up on this table. And we can click an experiment ID to find and learn into further detail what that experiment has been doing. Let's quickly revisit everything that we've seen today. As well as introducing AWS FIS, I'll show you how to define multiple experiment templates, execute experiments on a live system based on previously created templates, as well as collecting data to improve the reliability of our system. We're now nearing the end of our session, and I wanted to share other sessions from the event that I think are related to the content from today. Introduction to AWS tools to help you achieve operational excellence, get started with monitoring and observability on AWS, and how to reduce time spent on high-severity incidents. You join AWS Summit to learn, and you can keep learning beyond the summit with resources from AWS training and certification for DevOps. We offer over 45 online digital training that is available on demand. You can go deeper with 3-day instructor-led courses, DevOps engineering on AWS, and you can gain credibility and confidence with 2 related certifications. You can also explore labs, white papers, and other technical resources by downloading the AWS Ramp-Up guides. For more information, visit aws.training/DevOps. Thank you again for joining this session, and finally, I'll ask you to complete the session survey, as your feedback helps us improve our content and events.